much for the invitation. I am here to share a lot of the learnings that we've made over the years that I think that that could be useful to you. Um, 15 minutes is not a lot of time, so I'll do my best to run through this, and then we can skip a few things at the end. Um, what is very important is that our team is based in Norway. In Norway, we have access to a lot of data, and it is far more than in most other European countries, except for UK. Then I'll go through the summary of main learnings. The static versus the dynamic domain is incredibly important. I know that many of you here already knows this, but I just want to highlight that. And then I'll highlight it and show it with an example first from Norway, and then from Denmark, where we had an independent evaluation of some of the 18 sites or the 18 sites there. In the development of our maturation of these storage sites, it's a long process, and I'll just briefly show an overview just for context. And then I'll touch upon how we can communicate in a credible way the potential CO2 storage capacities as projects develop. And you'll understand much more when I get to that point. I've highlighted the closed structures in the open aquifers and then put a red line over the depleted fields. And that's because we don't deal with depleted fields. It's actually sort of the Norwegian authorities. They have outlined that let's go to the virgin aquifers first. So our perspective, as you said, it's about 20 people who have been engaged for the last 3.5 years. We have been screening the Norwegian subsurface, working in the shadows for many oil companies. We also work for authorities, and we have actually covered more than 100 potential CO2 storage sites. So we have learned quite a bit along the way. And remember, data here is of the essence, otherwise we couldn't have done this much. We have contributed to CO2 license applications, which both have been successful in several countries. And now we are taking the role as a sort of subsurface team for one of the license partners, and we're planning an appraisal well that's going to be drilled hopefully in the first quarter next year. We have covered the entire Norwegian continental shelf, so we know pretty much about all the aspects there. Our team also covers the different disciplines that are necessary in order to evaluate these sites. And especially I've highlighted reservoir engineering. I was talking to a young man before saying that the reservoir simulation skill is will be more and more important in the years to come. And we also have a drilling engineer, and that's why I'm so curious about the well integrity issues. So in terms of data, we have access to extensive and good quality data. I'm highlighting here a good example from the southern border or the border area between Denmark and Norway, where we have access to good quality data. And this is a spectral decomposition. And you can see the hexagonal fracture pattern that indicate a seal or shale. And then you see the linear stripes that indicate the sands that are coming from the north being dumped there. We are using this as lithology indicators in areas where there are few wells. Few wells is a good thing because then we don't have legacy wells and issues with well integrity, but we still have reasonably confidence about reservoir presence. In terms of data quality, then when we started investigating Denmark, then we got a little bit of a shock because we realized how spoiled we had been. In the data we could get access in Denmark, the data we could get access to was onshore data, and the quality is lower because of the seismic acquisition. I also want to highlight the structure here is the Havnsø site, one of those that will be awarded, or the awards will be announced in the coming weeks. And you see with the black lines, that's where there are seismic data points. The orange lines are the new acquisitions, and because it's onshore, then it's controlled by where there is roads. It means something about the confidence, the level of confidence, and also how fast projects can move depending on the data available. So it just means that we have a pretty good understanding of all of the licenses, what's in them, what the main risks are, both in Norway but also Denmark. We haven't touched upon UK yet. I highlighted the 18 structures of Denmark with orange, and you see that some of them, the ones that I've put names on, the Gasum, which is also known as the Norne project, the Havnsø, and the Ruby, are highlighted with gray text. Just note that they are not awarded yet. The letters are being sent out these days, and it will be announced in the coming weeks. I have much more to share about our learnings. We've actually documented on our website with plenty of blog posts. The one that I highlight in orange is where our reservoir simulation model example is going to be, and you can find it there again if you need it for your team. So the main learnings from our journey: many of the evaluations, they stop at the trap pore space. Remember, the most companies, they have a 25-year timeline. On the project, not 1,000 years. The size of the aquifer associated with the trap, it has to be significant. And I'm saying significant. We are talking about 1,000 square kilometers for making a commercial project attractive. The pressure front, it moves much faster than people think. And that's what I'm going to show in the video, how fast it moves. One of our where we had the steep learning curve was where we had the potential storage site, and we realized that the pressure front had moved more than 30 kilometers over a period of 5 years, where the pressure front reached the producing field. Coexistence is a very important issue. Don't expect one injector well to inject much more than 1 million tons per year. It's a really good rule of thumb when you assess the timeline, or how long time it will take to get to the targets that are stated. The cost of the first offshore CO2 storage well in Norway was about 100 million euro. And it was a very expensive rig, so it can definitely be done cheaper. But this is to give you an impression of the cost level that we're looking at. Offshore CO2 storage developments, they are expected to cost billions. And what I want to say with that is we really have to be careful when we select the projects that we want to focus on to make this a success. All right, static versus dynamic domain. Many of the national CO2 storage atlases that have been published, they are focusing on the static domain. And that's fine, but it's just that the CO2 storage capacity, when you try to understand or try to model, simulate, when you have an aquifer like this, you try to inject CO2 in a bottle that is already filled with water, then you have to increase the pressure. If you increase the pressure too much, then you break the seal, and you can't do that. So understanding how the CO2 plume behaves in the reservoir and the pressure front that moves ahead of it is extremely important. So we developed, usually building reservoir simulation models, it takes half a year and a lot of detail and a lot of work and a lot of money. So we developed this proxy simulation model, and it's just an Excel sheet, but it just means that we can assess and evaluate the number of wells and the storage efficiency in a number of days. And when we have done this and then build a reservoir simulation model, we're 10% off. So it's really a cost-efficient way. What you need to focus on first is the CO2 plume in the upper left corner. That is the amount of CO2 that is injected over a 50-year period. So it's not very much. The model is 50 kilometers long, the sandbox model, with a really good, nice aquifer. But look at the lower part. That is the pressure and how fast that is moving. If you look at the 10-kilometer mark from the injection starts, it takes 5 to 10 years before you actually get there. That has implications for license boundaries. That also means that whoever comes first to the aquifer, they have a competitive advantage by starting first, because then they can increase the volume space, which means that the Sleipner people, they have already started, and they have moved the pressure into the Trudvang license. This is important. So I'll speed up a little bit, run through this. The client came to us and said, can you please assess the CO2 storage capacity in this area? The atlas says 4.4 gigaton. And this was what we found. On the sea structure, one well with a dynamic modeling gives 40 million tons over a project lifetime. It pays off if you drill 3 wells, because then you can get to 120. And if you drill 12 wells, that's quite a cost, right? Then you can get to 320 million tons, and that's with a huge aquifer. If we go to structure number A, that is limited by faults, which means that you have a limited aquifer, not as small as the G structure, but it's still 1,000 square kilometers. Yet, one well will only give you 4 million tons, 3 gives you 10, and 18 gives you 30. No one's going to drill 18 wells to get 30 million tons down there. So in total, the base case scenario in that area was 200 million tons. So that meant that we actually, by going from the static domain to the dynamic domain, then we reduced the CO2 storage capacity by 95%. And it's about competing aquifers, really. So the study of Denmark, we don't entirely know what the reservoir quality is there. If it's most likely a fluvial gas information with marine inputs some places. If we are lucky, then it's all connected in one big aquifer. The total aquifer in an optimistic case is 21,000 square kilometers. What I want to show you is that when you're competing, then you can actually not add these volumes. So maybe it's up for the nations to select which projects that should move ahead, because it's good governance of taxpayer money. This is the result of the evaluation of the 18 sites in Denmark. So note that the 1 gigaton on one side, that's the scenario where sites have exclusive access to aquifer. Our evaluation is orange bars, and one of them goes above 200 million tons. If they are competing against each other, then on the case where it's 100 million tons with a stable line, then most of them will not go above the 100 million ton bar. But that's because they are competing with each other. So we should have someone to decide which projects that go ahead. As steps of the timeline, all the things that needs to go into place, Jim touched upon that, so I will not. But when we are evaluating CO2 storage capacities, we start at the National CO2 Storage Atlas, and it's a screening based on big assumptions. So we address the uncertainty. So this is the Stetin mountain in Norway. The top of it is the size of a football lane. It's pretty cool. As we move up the mountain and our projects mature, then we narrow the ranges because we have access to more data. We have the low as this number, so that's from your side, low as this number, base case scenario, and high number. And maybe we should be better at communicating this, because we have been approached by a client that said, someone went out and said there are 3 gigaton storage capacity in this basin. Why do you only have 200 million tons? Well, that's because they forgot to tell that the storage space was actually already filled with water. So I think it's of utmost importance that we are conscious about how we communicate our CO2 storage estimates, and also the maturity of the projects and how much we trust them. I've now put the Stetin mountain into an SRMS classification form that I want you to bring along with you. because I want us to communicate better what we expect and when we expect. And the thing is that when we get up to the top of the Stettin mountain, we can actually look at all the other possibilities. Let's skip my summary and recommendations, but